question number 70, it is on equivalence relations, the mappings, whether they inject, to prove that it's injective and also surjective.
Which one? Page 34.
Yeah, page 34, number 70. I didn't understand that line. Maybe if you can explain.
Okay.
I've also got a question on page 34, Doctor. The proof, they are actually looking at two elements, y and y dash, and they are all of a sudden y dash actually appears, but it hasn't been.
On which line?
The proof right at the bottom on page 34. This lemma 6.4. So there are two elements that we need to consider. Second line below the start of the proof.
Yeah.
Consequently, for y1 and y dash and y, an element of p.
Yeah.
I don't actually follow so nicely that particular argument with the two elements in p.
Okay. Okay, first for Charles, remember, so no, I did not possibly start sharing. So, can you see the...
Yeah, we can see it.
Yes, we can see the screen.
So this is...
And the recording, Doctor?
Yeah, I've started.
Okay, thank you.
So this is the set of all injections. With codomain B. So that means what are its elements? So, well, you can write an element like this, a pair, where it means that, where it means that F is an injection. Okay? Now, it says that you define, remember last time also we did this, we define an order. So we write something like this to mean that, so YG is also there, so it's this, is also an injection. So from the smaller to bigger, if there exists, so this means that there exists an H such that F is equal to GH. Right? So obviously it turns out that whatever you take, so if you have this, obviously you have the identity over here. Now remember a few facts over here. Properties of injections are required. So what is it? F is an injection. So a composite of two maps. So composite of two maps is an injection it implies that H is an injection. It is a property of injection, right? Further, this H is unique because if H prime be such that F is also equal to GH prime, then GH is equal to F is equal to GH prime. Now, G is an injection, so it's left cancelable, implies that H is equal to H prime. So, this is I don't need to say the uniqueness, but it follows, and moreover it follows that H is also an injection. So now the assertion 6.2a, it tells you therefore that XF is less than or equal to XF. Clear? Because you have already a one map from X to X, right?
Yeah, my problem was on defining that inequality there, what it meant to say XF and XG is less than, and then relating to a commutative diagram.
Yeah, so this is how I'm defining it. Now, this is the definition. Now, obviously, there is a as I explained last time, that there is a hidden intention. So intention is like this. So so what am I doing? The idea is that this is your B and this is your X. You are just having an injection. So possibly it is picking out a subset like this, right? So that is the subset, that is the range, that is the image, there is the range of F, and since this is an injection, it means therefore that in this part the function looks like this, right? If this was your X, in this part the function looks like this, right? Everything in this is the range, nothing is left over, and everything has a unique preimage. But obviously there are many elements in B which are no more the elements or preimages under this F. Okay? Now, the selection of this particular subset is more explicit. Here I cannot select that particular subset, but I can select, so if I were to say that this subset had only 3 elements, I can select several such. We can say that this is as if a representation of this of these 3 element subset, of this 3 element subset. Okay, there can be several other representations also. So there can be another 3 element set, and there can be another map, say X prime and F prime, and there can be many others, right? But I'm just saying each one of them is a representation. Okay, so that's what I'm saying. Now, how is the comparison now coming into the picture? So the comparison is, suppose you have chosen one representation of a subset. So let me take this one. So this is one subset. And suppose you have another so how do I take it? Let me say something like this. and this one, say this element goes to somewhere here. So you have another subset. Okay, so this was your x, this was your f, this was your y, this was your g. So I can see that there is a, so what I am trying to say, that I'll be able to find, see this extra element is the, so what do? I take this element, since I know there is a part of it where it is, so I go back to the pre-image of this, so therefore H takes this element, so you can see what I am doing. H exactly does this mapping. Okay, so this is my map H. Okay, so H, but you see H doesn't map anything to this extra element which is mapped over here. So you see the idea behind this commutation, that H is mapping this element over here, this is over here, and this is getting mapped to these elements, corresponding elements. So that's why I am saying your F is nothing else but G composed H. That is the meaning of this. Whereas there is an extra element over here, this one, which H doesn't take care of. And that corresponds to this extra element which was in the bigger subset. So now you see that this idea kind of represents the notion of having Y having more elements, or having many more things, or being stronger in that sense than X. If you can find a map from X to Y which makes this diagram to commute. Yeah, is this clear?
Means since Y is having more elements, which makes it not to be a surjection.
Which one is a surjection?
Since Y is having more elements, some not mapped.
Yes.
Can we call it as it's not a surjection?
Remember, surjection is the name of a property to a function. So which function are you saying to be a surjection?
I think G does not leave X, but still G leaves extra elements. The extra elements are mapped there.
Yes, so G is not a surjection, it is still an injection, but you see, this extra element is not from this small subset that was going to represent X. X was representing this small subset, right? Inside.
Okay.
G
Yes.
is representing something bigger because of this extra element outside.
All right. Yeah. Now I see it.
Yeah? Okay?
I see it. Mm-hmm.
So that is the idea behind saying that G is kind of having or Y is having more elements than X by this order. So this order, this less than that we have defined, kind of reflects the idea that there are more elements, or let me say more in Y than in X. Okay? That is the idea that is being represented by this relation. Yeah? Okay?
Yeah, it's clear now.
Okay. So now you see, obviously x has more elements than x, because that's true. So it's reflexive. So the relation is reflexive. So obviously, what am I doing by making this? I'm actually saying that I am taking this, formally speaking. Remember, this is nothing else. This is just given by this pair, xf and yg. So this is a subset of so this is relation, right? This is actually a relation on inj B, on the set of injections on B, right? What I am saying is that this relation is reflexive. So that is the assertion 6.2a. That the relation that I have defined is a reflexive relation. Okay? So that's what, so in 69, for instance, it defines a relation, and it says 6.2a says it's reflexive, and then obviously this, if you have, so I am not doing, so if xf is less than or equal to yg is less than or equal to zh. So this means that there exists a p from smaller to bigger, there exists a q, so obviously there exists this composite, right? So this automatically tells me that xf is less than or equal to zh. So that's B. So that means these two say that this relation is reflexive and transitive.
And the transitive, okay.
So if you remember what we did in relations, this means that this is a pre-order. So this is a pre-ordered relation on injections. Now partial order, you have to speak about the antisymmetry, but that is where it fails. So that is exactly part C, which says that suppose you have so this is your xf. So suppose you have xf is less than or equal to yg, and that is also less than or equal to xf. So this means about this p, so you have f is equal to gp, right? I should have, as I was doing, there exists a p and there exists a q, right? Now this one, for this one, there exists this q such that g is equal to fq. Now you have to do some calculations. So f is gp, But G is FQ. So what are you having? So this is telling you, you can also write F as F identity of X is equal to FQP. Right? Now F is an injection, so it's left cancelable. So you have QP is equal to identity of X. So similarly, PQ is identity of Y. So you see that if this happens, so then it tells us, so XF less than YG less than XF. This implies that there exists a bijection so PQ is this and QP is this, tells you that Q is nothing else but P inverse and P is a bijection. So there exists a bijection P such that F is equal to GP. Right? Clear?
Yes, Doc, is clear now.
Now you see, if you take the other side, suppose if there exists a bijection with this, then obviously, if this happens, then obviously FP inverse is equal to G, because P is invertible. So that means you have the other side, right? So there exists a bijection like this, it tells you only this part, the bijection part also tells you this. So what I say is, in fact, I can say something like this, right? So that is, this is not only an implication, but an if and only if. So that's exactly part C. Now, part D tells us that this is an equivalence relation. So what is the relation? You are saying XF is equivalent to YG. If, so what is this? There exists a bijection P such that F is equal to GP. Right? That's, I believe that's how I did it. Yeah. So you can immediately see that this is an equivalence relation. Why? Because XF, see, I can immediately write this. This is actually, what does it mean? This actually means XF, this previous statement over here. It is this and this, right? Right? This is exactly from C. Now this is an equivalence because obviously XF, if you take XF equals, so obviously you have, let me copy this. So this is trivially true, right? Because I have already shown part A tells me this. So there is nothing more in this. Right? Yeah?
Yes, Doc. Yes, Doc.
Yes.
Now, suppose XF is equivalent to X prime F prime. And YG, so let me write these equivalences, is equivalent to Y prime G prime. And say ZH is equivalent to Z prime H prime. Now observe, if you have xf less than or equal to yg, so does it mean that x prime f prime is less than or equal to y prime g prime? Yes or no? Yes or no?
Yes.
Yes. Why? You will just use transitivity and this definition, because this definition tells you that x prime y prime is less than, you can plug in an x prime y prime here, x prime f prime, and you can plug in y prime g prime here, right? Correct?
Yes, Doc.
Then this is just transitivity, which is saying that this is happening. Okay? So, the crux of the matter is that this relation automatically then turns out to be, equivalence relation. Why? Because suppose xf is this, and this is also equivalent to say yg, then automatically you have told me therefore xf is this, because you will just put in this means this as well as this means this as well as this. So transitivity will tell me this. Okay? Now, if you have xf, so this tells me it's transitive, and obviously the way you have defined it, the symmetry is immediate. The symmetry is immediate. Remember, this means actually both of them. So this tells us that it is automatically symmetric, right? So it is symmetric, it's transitive, it's reflexive, so it's an equivalence relation. So now what happens? If this is an equivalence relation, then what is happening? If this is the set of all injections in B, equivalence relation is going to partition it. What happens? If you take any two elements over here, they are equivalent, right? But there can be an element here which is maybe, I don't know, it may not be, they may not be always related. So it essentially tells me that the injectives into B are partitioned into equivalence classes, and your factorization theorem that we did, remember, for any map, if you have any map, what is your factorization telling you? You have your surjection
followed
by an injection, right?
Yep, that's right.
Now this injection was also made very explicit by taking this to be the range of f, right? So the range of f was made to be a subset of y and so on. Now, so therefore, if you take, for instance, this xf, so you already tell me that this is an injection. And you are going to tell me that this is your, I don't remember how did I represent this. This is fs and possibly fi, right? Let me use some others. So let me say this is E and M. Okay, so this is injection and this is a surjection. So I am taking this xf to be this, one of these. So let's see what happens. If you tell me f is equal to me, now f is an injection, so a composite is an injection, it tells me that E is also an injection. Right? So, what does it tell me? E is an injection, but I had taken E to be a surjection, so therefore E is a bijection. Right? So you see, if you, each one of these is actually equivalent to this, to a very special one. Let me, how do I write this special one? Let me make it just bold. Say, this is the special one, range of f. Over here also you have a special one, which is range of G. Right? So you see, in each one of these equivalence classes, there are very special representatives. Okay, and now I am drawing the same color. So each one of these equivalence classes has a very special representative which is explicitly a subset. But as far as our counting principles, especially explained in this context, goes, it tells us that xf, any representative over here in this equivalence class, has the same number of elements as this particular subset. Same over here. Yg has the same number of elements as the range of G, and so on. So the number of elements kind of a thing. So what does this equivalence relation signify? This equivalence relation kind of signifies the number of elements in a subset of P, or which we will call, instead of saying or more, or the cardinality of a subset of P. Okay, so it tells us, remember one particular equivalence class is for B itself, and here that range of this is B. So this is that special element, right? So it tells us, so this equivalence relation tells us, or grades this, you can think of this gradation. Obviously, another thing I didn't write over here. So you have this B identity, you have, this is an, obviously this, and remember I said I'll denote by IB the unique map from the empty set to B. Right? You will say, how do you know that this is 1 to 1? Okay, let us see. So here is another proof. So the fact for every set B is injective. And it is surjective if and only if B is this. So what's the proof? The proof is very simple. Strangely speaking, remember, what do I have to show? I have to show, to prove injectivity, I have to show it's left cancelable. Right? Okay. So let's see. Left cancelable means suppose phi u is equal to phi. So you need to have some set, say x, so assume now in fact you don't need to assume, because this is a map from x to b. Sorry, I didn't prove something, sorry. Now since u and v are maps from a set to the empty set, then u and v are actually the empty. So therefore, since u and v are both subsets of this and are functions, it must be, remember we did this earlier, it must be that x is the empty set. From a non-empty set to the empty set, you cannot have a function. So since you have given me it to be a function, so x must be the empty set, and in that case u and v is nothing else but the identity function on this. So immediately you know, you assumed this and you have also proved this. So it is a IB is an injection. And when you are saying that it is a surjection, so if you are saying that if IB is a surjection, IB is a surjection, if and only if every surjection has a right inverse, there exists a function such that IB composed G is identity of B. Since G is a function, again the same study, G is a function with codomain B must be the empty set, and hence G is identity of the empty set, which is equal to I of B. Okay, so that tells us, so that therefore B is equal to the empty set, right? So you see, these functions are always this. So you have very particular. So coming back, you have very particular. Always you have very particular equivalence classes. One is the class for B, and the other is the class for the empty set. And for every other subset, you have one such class, right? So this tells you the notion of cardinality of each subset of B. So is this clear now?
Yes, it is, Doc.
Are you?
It's very clear.
Huh?
Can
Are
I
you?
just have one question, Doc?
Yeah.
The fact that if you look at this on this slide here, we've got x and f equivalent to x prime and f prime.
Yes.
So obviously these two sets, the x and the x prime, are different, isn't it?
Yes.
Are different sets.
Yes.
But they actually have the same number of elements.
Yes, exactly.
Cardinality will be the same.
Yes.
Okay.
Yeah. X and x prime have the same number of elements, and it is actually the same number of elements as range of f.
Okay.
Yeah. So you can see, if you take an arbitrary say, so we can do this, we can run this example for a finite set. So you have, for a finite set B, say let's take 1, 2, 3, 4. So for B, you therefore have exactly 5. So the empty set, so the 0 number of elements, 1 number of element. So you the partition looks like this. 1 is for the, so which contains the empty set, that is the 0 number of elements. So I'm just writing these are all the partitions. So you can see the whole lot of things. So you have 2 over here, you have this over here, this is nowhere connected with this, right? And all possible singleton elements, they are all there. All possible 2-valued sets, they are all here, right? All possible 3-element sets, they are here, and so on. And so B has, here there are all 4 elements. So you can see how this cardinality business is trying to tell us the cardinality of this is same as this, is same as this, and that is what you say 1. Okay? And well, there is an abuse of symbol, obviously, and but you must first accept that the cardinality, the notion of cardinality, which we call as 1 or call as 2 or 3, it is the idea that it represents a typical thing, a set with 3. When I say cardinality 3, it means it says it represents a set with 3 elements. Okay? So cardinality itself is an equivalence. It's an equivalence class. Okay? In this way. Right? Clear? Okay?
Yeah, it's clear. But then
Yes.
the way you presented it now looks like a power set now.
It's not the power
And
set.
then, now
Remember,
when it becomes a power set now, the subjectivity becomes questionable now.
you see, it's not the power set because it's not the power set. There's a little bit, there's a difference. In the power set of this, there are 16 elements. Right? But here itself, in this equivalence relation, in this set, there are as many. Give me a set, I will give an element over here. How? You have given me a set A. Right? I will take this singleton A. That is also there. Do you see the difference now?
Yes, yeah, I can see it now.
So it's not exactly the power set. It is, well, the power set's elements are obviously there, but this is, you can see the difference. It has, intuitively speaking, I am trying to say is this equivalence class has infinitely many elements. Although B has only 4 elements. But this, so in other words, the set of, this is, remember, this is the set of all injections coming into B. And there are infinitely many injections that can come into B. But when of these injections, some of them are related, some are not, but they have only as many different equivalence classes, well, as the number of elements of B, plus 1 possibly, yes, with this empty set, yes. Yeah? Yeah, so it is kind of packaging several things, several singletons, all come to be equivalent as an injection into B. Okay? Alright? So we will often call any one of them to be a representative of cardinality 1 in B. So if I take this set, for instance, this is a representative of the cardinality 1 in B, or even this. Okay? But if I take, for instance, as I took here, now this, the difference between this and this is both of them are subsets of B, but this is not a subset of B. Okay? So, what I'll say for this one, I'll say this is a representative, or this is a representative of the cardinality 1 in B. So, that extra in B will just tell me that it is, I've taken a subset, a proper subset of B. Whereas this is a representative of cardinality 1, well, this is not in B. Okay? So there are several instances of representatives, some in B, some not in B. Clear? Clear?
Yes, yes.
Okay.
Clear.
Okay. So that's essentially your 70, right? So that's what I wanted to say, that it is an is in 1-to-1. If the factor set is in 1-to-1 correspondence with the set of all subsets. So what is the correspondence? Well, so that's exactly what I did over here. That's how I did. Why? What's the game? So I take injections of B and I take a subset of B, and I take XF and I was taking it to range of F. Okay, and I just needed to show, so I needed to show that if XF is equivalent to X prime F prime, then range of F is equivalent. I didn't say what is an equivalent over here, but there exists a bijection from range of F to range of F prime. Yeah? And that's exactly the meaning of this, right? Clear?
It's clear now.
Yeah. So that's what I was saying. So UX, as I said, so that's the range of it. So you see, this now tells us about this now kind of so this injectives and this given a set B, we can make a counting. We can count in this way. In this, we have not still made up a standard. Okay, so we will not until very late. We will come up very late with a standard against which we will compare. But we can make this comparison between subsets. Good. Now the next part of the story is that which is lemma 6.4. Yeah, lemma 6.4. In fact, I think I proved last time in a very, very implicit way. So you have this E. What is it? PQXY. And what are the rest? U and V. Okay. And this is surjective. This is injective. I'll come back to that proof. Now you told me that E is surjective, so it has a right inverse. So E composed G is identity of Q, right? Clear? Because E is surjective. Yeah?
Yeah.
So now what I am taking is, I am taking this W to be UG. So that's how I am taking it. Okay? So now with this, and obviously you had already given me this VE is equal to MU, right? That was given. Now you have taken this, so that becomes your W. So since you have taken this, now let's see. So WE is UGE But U, did I make a mistake? UG, yes, and EG, yes. UG. Aha, sorry, I'll come to it later. So, firstly, this one. So, you have VE is equal to MU. VE is equal to MU. Okay. So, VE is equal to MU. So, this tells you VEG is MUG, right? But this tells you V is MUG, but UG is your W, is equal to MW, and therefore, so V is equal to MW. So you have, so therefore, MU is equal to VE is equal to MWE, but your M is an injection, so it tells you U is equal to W. Okay? So, with this choice of W, you have V is equal to MW and U is equal to WE, and if you have another such, if W prime is another such that V is equal to MW prime and U is equal to W prime E, then V is equal to MW prime is equal to MW implies, since V is an injection, that W is equal to W prime. Right? So there is only one such choice. So last time I did this proof. Now let's see how does the proof that I have given works. Now, what am I doing over here? Here I am saying take a Z in Q and I take a member in the Y from E inverse Z, right? So you have taken a Z in Q and Y in E inverse Z. Now let's try to figure out what is this. This is P, this is Q. Remember, your map E is a surjection. So it looks like this. The stock diagram looks like this. Let me, and there is no other, right? Right? Nothing is left over on Q, right? That's your picture of E.
Yes, because it's a surjection.
It's a surjection. Now, how do you choose this G? you choose exactly one such elements. Right? So, if you had two elements, you would choose this y prime and y. Okay? That's exactly your choice of G. Now, you can take another choice. Instead of, you could take a y1 here. And similarly over here. So that means the moment you change one of it, you change your choice of G. Right? But this proof tells me whatever be your choice of right inverse, that doesn't matter. But when you composite it with U, that composite remains to be the same. Yeah? That's the essence of this proof. So, that's what I was doing over here. So now you see how these two proofs are related. Right? Choosing an element in the pre-image is essentially, so this part is essentially means selecting a right inverse. Right? So remember, each choice you have to make for all of them. So for all of them, making a choice of this pre-image is actually selecting a right inverse. Okay? The moment you make a change in one of those choices, you have changed your right inverse. But the proof above tells you whatever choice of your right inverse G may you take, the composite with U gives a unique map. It doesn't depend on the choice of your right inverse. That's what this proof is essentially saying. So therefore, it doesn't matter how you choose it. So now you see, when you have these two proofs at your hand, you see how the proof that I had written originally is a little bit messy, trying to making it explicit. Whereas if I use this functional composition and this functional properties, how simple and clear cut it becomes and what it tells us. Right? Do you see this?
Yes, Doctor.
Yes.
Yeah. So that's why I usually like this. I hope Stanley was here today. So explicit sometimes makes it apparently clear, but it is very messy. And this implicit, it's seemingly hazy, but actually it is not. It just ignores those messy computations in between. Yeah, and gives you the answer straightforward. So, okay. So, that's lemma 6.4, and lemma 6.4 is just used in showing that the factorization is essentially unique up to isomorphism. Yeah?
Yep.
Yeah. So, it's already an hour. I can still continue, but since I don't want to do the proof of Schroeder-Bernstein again today, especially because Stanley is not here, and let me what do you say? Let us postpone it to the next day.
That sounds perfect, Doc.
Yeah, it's okay with me.
And
Yeah,
then
but
yes, one minute. Just look into section 7, try to go through the proof, and especially this proposition 7.1 and this remark 7.2, where something about this naturality again comes into the picture. Yeah? Okay?
Okay.
Yeah. Charles, you are saying something.
I wanted to talk about the uploading the videos. You forgot to upload the last week one.
Oh, yes. Yes. Okay, I will send both the links of the videos today.
No, it's all right, Doc.
Okay. Any other questions? Any further questions on what we did today or so on?
Yeah, let's just postpone so that also Stanley would be with us.
Yeah. Okay.
Okay. All right. Thank you very much, Doc.
Thank you.
Thank you very much.
Thank you
for
Keep
everything.
well. Yes. Yeah.
Bye.
Thank you, Dr. Partha.
Thank you. Keep well. Yes. Bye.
Okay, goodbye.
Goodbye.